Introduction to electric charge. So electric charge, and I'm just going to refer it to as charge in general. So as you can see there, it utilizes the symbol Q. However, you can also utilize a small q as well, and you're going to run into both of these, okay, throughout as you study charges. Now, this is actually a fundamental physical quantity that we have. Now, fundamental physical quantities, the ones that you've studied before, were only really 3. And from these 3, we were able to derive quite a lot. So if you recall, the original, when you started off with physics, you had fundamental physical quantities of distance, time, and mass. And from these 3, you were able to derive quite a lot over the duration of the various chapters that you studied. So things from speed or velocity, accelerations, for example, forces, for example, energy or work that you've had. You can talk about pressures, you can talk about power, you can talk about density, okay, temperature, etc., etc. So all of these quantities really were derived in one form or another from these fundamental physical quantities, right? So that's what we had. Now we're adding a 4th fundamental physical quantity, and that's going to be charge. So for this charge, which we do experience and we see it in nature, so we have a particular metric standard unit, so that's the SI metric standard unit, and we use Coulomb as the actual metric standard. So for example, distance, the metric standard was meter, time was seconds, mass was kilograms, right? For speed, meters per second, acceleration, meters per second squared, etc. So we all have metric standards. Well, for electric charge, we also have, and that is coulombs, right? So now there's one other particular unit. Luckily, there's not too many units within here, but coulomb is the one that full out dominates for us as a metric standard. We also have some other ones, which I will mention briefly, okay, in just a moment. So this coulomb that you have, so it's basically spelled in this way, and it is named after a scientist. Now, charges that we have, what is interesting is that charges kind of come in 2 forms. This is what we have been able to observe. So there's 2 different forms of charges. And these particular charges, so there's 2 types of charges, and these charges, if they are alike, they attract each other. If they're alike, they repel each other. Okay, so if they are alike, they repel each other. This is what we notice. And when they are unlike, then they attract each other. Now, because of the fact that many students have kind of studied chemistry or in sciences in some way, soon as you talk about repel, okay, and attraction, right away electrons and protons come into play. And indeed, this is exactly where these charges are coming. Now, scientists way back, they didn't know of electrons and protons at the time. They weren't discovered, but this is where these charges are coming from. So again, if they are alike, they repel. If they're unlike, they attract. And now what is very interesting that these 2 types that we have named them. So a positive charge and a negative charge. This is purely by convention, right? So we name positive and negatives, okay? And it's a complete convention that we have. So we do have a positive charge and we have a negative charge within it. So if you have 2 positive charges, well, then they're alike and they're going to repel each other. If there's a positive charge and a negative charge, they're going to try to attract each other, okay, in some particular way. So we have these 2 types of charges. Now, these particular charges, what is also very interesting is that they are quantized. So they are discrete. This is unlike, for example, distance or time, right, that we have. So as you're pushing through, okay, so the quantization effect of charges, this is what it actually means. If you would take a number line for distance. So if I would do something like this and I told you, all right, so this is distance. You know, you can mark one point and then you can mark another point within here. But you know that there also is a distance that exists, and it could be anywhere between here, right? So if you have, you know, from here to here, if that's a distance, well, from here to here is also a distance. Well, it turns out that if you're talking about charges, and this is what's really neat about it, so if you now change this back into charges, well, charges are quantized, and there is, at least up to this point, what we have observed, the smallest amount of charge. And that smallest amount of charge, okay, so let's say if this is it, and this, you know, I'm going to name this as an electron, so electron with a little negative over here, okay, so this would have been 1 in the smallest charge possible. And this is equivalent to, and in terms of coulombs, it is 1.602. Now, it does have more significant figures, but I think 4 significant figures is more than enough. Sometimes you even have less as you are studying this, times 10 to the negative 19 coulombs. So coulombs is the SI standard, and it's used for convenience. You know, 1 electron, you know, we could certainly use, and sometimes you do see this right here. So you might see the unit for charges as E, which just means representation for 1 electron charge that you have, but it's just super tiny, right? So that's what you would have in there. So for practical purposes, we've actually kind of, not we, but the scientists have decided to stick with coulombs, okay, because it's a little bit more convenient. But what I'm trying to say with regards to the quantization is that now the next charge that you have, so if you were going right here and you were trying to do this on a number line, there is no charge in between here. So if this, for instance, was 2 electron charges, which would have been, you know, 2 times this, so you would have multiplied this times 2, there is nothing in between here. So you cannot say, oh, I have 1.5 of an electron charge. No, it's either 1 or it's 2 or it's 3. So it's an integer-based quantize. So quantization, that's what it means. It means discrete. It jumps from one to another and it continues on. There isn't actually anything in between, not something that we have observed at least to date, okay, that I'm aware of. So that's pretty neat and interesting. Now, please don't think that, you know, the charges are only based on electrons. So as we said, so there are charges that are positive and that are negative. So we have, by convention, named electrons as the negative charge. And what we've done is we've named protons. Okay, so within here, so if you have 1 proton, we don't really write 1 proton in this way. You know, you might certainly still write it as an E, and you might make it positive like this. So that would have been just 1 charge, but now it's positive. So what this means is that our charges, so this 1 electron, to designate it, this is just the magnitude, but this would have been negative in here because of the fact that by convention, we assume that the electrons are negative. And this, on the other hand, so if you were mapping this out, this would have been a positive 1.602 times 10 to the negative 19 coulombs. Notice that they carry the same magnitude. And very often what we will do is this. We will say that the charge of an electron, like this way, and we will put magnitude absolute values around it, and this would have been just 1.602 times 10 to the negative 19 coulombs. So that's what it is. But if you want to make it specific and you want to know if it's a positive or a negative charge, you do typically put either positive or you're going to put a negative to let someone know, right? So that's what you have. Now, in this case, as you can see, because it's times 10 to the negative 19 coulombs, it's super tiny. So there's a lot of these electrons or protons in terms of charges that you would have and been able to kind of put into 1 coulomb. So 1 coulomb is actually quite a bit of number of electron charges that you would have in there. So what I am referring to is the following. So if you wanted to try to see in here, so for example, if you take 1 coulomb of charge, now if it's positive or negative, okay, so in this case, if it's positive, so we can say, okay, so how many protons would that be? Well, so within here, so we would have to do the following. We would have to say, all right, well, 1 proton charge, or simply, okay, so if we would write this out in terms of electrons, so this would have been E but positive, is equivalent to 1.6 times 10 to the negative 19 coulombs. So notice the coulombs will cancel, so now all you're doing is a unit conversion in terms of the electrons themselves, and you can check, you know, how big would this be? Well, so this is just 1, and then it would have been divided by, I'll put it in brackets here, 1.6, okay, I'll put 0.2, okay, in there. So this right here, I'll put 1.602, and then multiply it by 10 to the exponent. So I'm going to put that in there, negative 19, and you'll see it, it's enormous. Right? So this is how many, I'm going to just kind of round this in, 6.24, 2, for instance, so to 4 significant figures, times 10 to the 18 of these. So that's quite a lot of protons that you would need to make up 1 charge of 1 coulomb that you would have. And if it was negative, then you can ask the question, how many electrons would that particular be? So there we have it, okay? So we have positive and negative charges. They are now, so now we know as time has moved on, so they are related towards electrons and protons in terms of charges, okay, that we have. Now, we don't actually experience, or at least they're not stable enough, not long enough, that there are other particles that might carry these charges. Now, if you have studied, for example, nuclear decay, you'll notice that, there are some particles and they might be of a particular charge. However, they don't last very long. So kind of the stable charges are actually coming from electrons and from protons, just so that you know that. So now, one other item, okay, or a couple of other items that I would want you to know is what is very interesting is that these charges, okay, that we have, if you have a charge, so whatever that charge is, so let's say, I'm going to call this Q1, so let's say this is some charge over here, and then, let's say maybe there's another charge, Q2, and it's somewhere over there. So maybe it's a combination of these electrons or protons, okay, and then it's stuck here. Now, when we do have these charges, or electrons or protons, and they're fixed, so they're actually not moving. So you may recall, and this is if you've studied enough of the physics, so you will certainly recall, you know that if things are stationary and not moving, then we call this static. And very often you will hear this word static electricity. And static electricity just means that the charges themselves, if they do exist, are static. They're kind of non-stationary, or at least we're assuming that they're stationary. So that doesn't mean that you can't move them from one place to another. But whenever we use the word static electricity, we are referring to the fact of charges that are not moving. All right? So that's something that you should know, because you're going to hear that word quite a bit. So static electricity, you're going to be talking about, you're going to be trying to find out and calculate various charges for static electricity that you have. And this kind of static electricity, of course, can be both with respect to positive and negative charges. All right, so that's another item. Now, the final item that I would want to be able to mention before I kind of close off this video is I do want you to know that charges are actually conserved. Now, you may remember from studying energy. So when you were talking about energy, you may recall the conservation of energy. So that energy cannot be created or destroyed. It can only be transferred, right, from one form to another. So that was a statement with regards to energy. Well, it turns out that charge, okay, abides to the conservation as well. Now, it's not a conservation of energy, it's the conservation of charge. So when we say charge is conserved, that means, again, you cannot create or destroy charge. You can only transfer it, or the charges can combine, so as you know, so electrons can, maybe bind in with another proton and they can cancel each other off, but you can't actually create them or destroy them in any particular way. So that is pretty neat, and you should know that charge is conserved, which means whatever you start with is the amount of charge that you end with. It doesn't mean that the overall charge is the same, so because the charges can transfer from one form to another, but what it means is, for instance, if you have a charge of 3 coulombs to start with, okay, then at the end you're going to have 3 coulombs that you ended off with. Now this 3 coulombs can be separated in some particular way, so maybe it's 5 coulombs over here and negative 2 coulombs over here, so when you add them up you're still going to get 3 coulombs, and then something might happen that maybe there is some transfer, okay, that you would have. And in this way, so what might happen in order to still conserve the charge, the 3 coulombs in total, so maybe let's say that you have kind of lost the positive one, so maybe you went to 4 coulombs in here. Well, what that would mean is that the other one would have been just negative 1 coulomb, and it would have been conserved overall. So there you have it. So that's kind of the introduction to these charges that I wanted you to know. So now you know the quantized charge of an electron or a proton. So please remember, they are equivalent, they're equal to each other. All right, so that's how we kind of designate these. And if we want to make it specific, it's positive or it's negative. So that's what we have in there. And we have these 2 types of charges, and we have the metric standard that we use, which is the coulomb. All right, thanks for watching. Welcome to electricity.